Welcome to the deep dive. Today, we're going deep into the world of fluid dynamics.
Droplets.
Droplets. Yeah, you might think, what's so complicated about it? A little bit of water, right? We've got this academic thesis on modeling droplet deformation, and it shows just how intricate these tiny wonders can be.
Absolutely.
So we'll unpack how air and water interact, especially when things get turbulent. High Reynolds numbers.
Yeah.
We're going to hear about cool mathy terms like triple deck structure and lubrication approximation. Get ready. We're going to unlock the secrets of these little marvels.
It's true. Even the simplest droplet can hold a world of complexity. This thesis takes on the challenge of modeling how a droplet changes shape.
Okay, I'm all about breaking down complex stuff.
Right.
Tell me more.
They actually model it in two stages. First, they imagine air flowing over a solid shape.
Like a frozen?
Yeah, like a frozen snapshot of a droplet.
Snapshot.
And then they add in the water flow and how it interacts with the air.
So they start simple. And then crank up the complexity. It's lever, but
Yeah.
air and water are pretty different. Density-wise, how do they factor that in?
That's a good question. The density difference between air and water is huge, about 828 times.
Wow.
The researchers use this to their advantage by initially treating the droplet surface as if it were solid.
Okay.
It makes the early stages of modeling more manageable.
So they're simplifying the problem
Yeah.
by initially ignoring the messy mixing of the fluids.
Yeah.
Makes sense.
Yeah.
But they can't ignore it forever.
Right.
How do they eventually bring those interactions back in?
That's where those famous Navier-Stokes equations enter the picture.
Okay.
These equations govern how fluids flow and are key to understanding the intricate dance between air and water in this scenario. But before they jump into the complexity of a deforming droplet, they need to make sure their mathematical tools are up to the task.
I see. Sort of like a test drive before the real race.
Exactly. They use a classic problem in fluid dynamics called the lid-driven cavity. Imagine a square box filled with fluid, and the top lid of this box is moving at a constant speed. This simple setup creates complex flow patterns within the box, and by accurately simulating this, they can be confident in their methods.
So a controlled environment to make sure. Their tools are sharp.
Exactly.
What kind of tools are we talking about here?
They're using what's called a finite difference approach and a grid system. Think of it like dividing the space into a bunch of tiny boxes and then using math to figure out how the fluid behaves in each box.
Yeah.
It's computationally demanding, especially when they try to model flow at high Reynolds numbers.
Right, like trying to predict the movement of 1,000 butterflies flapping their wings.
Yeah.
Okay, so once they validated their methods, how do they tackle the water droplet itself?
Right.
You can't exactly make a square box out of water, can they?
That's where things get even more interesting. They start with what they call a circular seed problem. Imagine a perfectly spherical droplet just hanging out in the air.
Okay.
It's an idealized scenario, but it helps them understand the basic flow patterns inside the droplet.
Using some elegant math involving
Trigonometric series.
that takes me back to high school math class.
Yeah.
What do sines and cosines have to do with?
Droplets. Well, these functions are great for describing anything that repeats or oscillates. And in this case, they revealed that the water inside the circular seed is in a steady state flow, not changing speed or direction over time.
Okay.
But a perfect sphere isn't very realistic, is it?
Yeah, raindrops aren't exactly known for
Right.
their perfect spherical shape.
Right.
What do they do to get closer to reality?
To get closer to a real-world droplet, they move on to a square droplet model, a bit of a mathematical mind bender.
Okay.
I know. It helps them validate their numerical methods in a slightly more complex shape, and it reveals something quite unexpected. The water inside the square droplet keeps getting faster and faster over time.
Wait, hold on. Didn't you say the circular seed had a steady flow? Yep. Now we've got water accelerating inside a square droplet. That seems counterintuitive.
Exactly. It's a surprising finding that challenges the initial assumption of a steady state flow and shows just how dynamic these seemingly simple systems can be. But a square droplet is still a bit of a stretch. What's the next step in their modeling journey? They take it a step closer to a real droplet with what they call a semicircular droplet model. Think of a raindrop clinging to a surface that kind of shape.
Okay, I can picture that.
Yeah.
And what happens inside this more realistic droplet?
Well, the key takeaway is that the velocities within the semicircular droplet, just like the square one, continue to increase linearly with time. The water just keeps getting faster.
Wow, that's really interesting. It's amazing how something we see every day, like a raindrop, can be so dynamic. So they've modeled the air flowing over the droplet and the water flowing inside it?
Yeah.
How do they put it all together?
They combine the air and water flow models, focusing on the early stages of droplet deformation. When the shape is still roughly semicircular, a key finding from this combined model is that both the pressure and vorticity, that swirling motion inside the droplet, increase over time.
Okay, so things are getting more intense inside the droplet, but I'm guessing this early stage model has limitations.
Of course. One of the main limitations they acknowledge is the idealized interface condition they use in the early stages.
What does that mean exactly?
They make some simplifying assumptions about how the air and water interact at their boundary. This works well initially, but as time goes on and the droplet changes shape, those assumptions start to break down. Think of it like assuming a flat Earth. It works okay if you're only traveling a short distance, but once you start going further, you need to account for the curvature.
Right, those little details become more important over time. So the model's accuracy decreases as the droplet deforms? What do they do to account for that?
That's where the triple deck structure comes in. It's a much more detailed model that helps them understand the later stages of droplet deformation, when those early stage assumptions no longer hold.
Okay, that name has come up a few times now. Can you explain what that triple deck structure actually is?
Imagine you're looking at a droplet on a surface. Right at the point where the air, water, and the surface meet, there are actually three very thin layers interacting. It's like a microscopic layer cake. The triple deck structure is a way of mathematically describing these layers and how they influence each other. It helps explain why the early stage model breaks down. The interaction between these layers becomes too complex to ignore.
Ah, so it's like using a super powerful microscope to zoom in on that point of contact and see all the intricate details of how the air and water are pushing and pulling on each other. I remember you mentioned a lubrication approximation too. What's that about?
That comes into play when they want to model a droplet completely encased in a boundary layer, like a tiny droplet nestled within the thin layer of air flowing over a surface.
I'm starting to realize how many different scenarios they're looking at. It's really impressive how they can model all of this.
It is, and they don't just stop at the modeling, they connect their findings to real-world applications.
Okay, now we're talking, give me some examples. How can understanding droplet deformation impact our lives?
Think about airplane icing. Ice building up on the wings can be really dangerous, so understanding how droplets deform and freeze on a surface helps engineers design better de-icing systems.
So the next time I hear the pilot talk about de-icing, I can thank fluid dynamics. What about other applications?
Fluid dynamics also plays a huge role in agriculture. Think about crop spraying. The size and shape of the droplets from those spray nozzles can have a big impact on how effectively pesticides and other chemicals are delivered to the plants. Too large, and they might run off the leaves, wasting the chemicals. Too small, and they might drift away in the wind and miss the target.
Right, so there's a sweet spot where those droplets are just the right size and shape for optimal delivery. It's like Goldilocks, but for droplets. It sounds like understanding fluid dynamics is crucial for efficient and environmentally friendly farming.
Exactly, and the applications don't stop there. Inkjet printing, where precise control of tiny ink droplets is essential for high-quality images, also relies on understanding fluid dynamics. Even in medicine, researchers are developing microfluidic devices that manipulate tiny droplets for drug delivery and diagnostics.
It's amazing how these same principles that govern raindrops can be applied to such cutting-edge technologies. This deep dive has really opened my eyes to how important fluid dynamics is, not just in some abstract scientific sense, but in everyday life.
It really highlights the power of understanding the fundamental principles of nature. And the researchers didn't stop there. They also looked at what happens at the microscopic level when a droplet interacts with the surface.
Oh, tell me more about that. What's going on at that tiny scale? So we've talked about the big picture stuff like airplane icing and crop spraying. But what about the nitty-gritty details? What did the researchers find out about those microscopic interactions?
They zoomed in on a droplet interacting with a solid surface, and they used a clever analogy to simplify things. A problem involving dry, wet, and dry regions along a wall.
Okay, I'm picturing a droplet on a surface. So that's the wet part. But what about the dry parts?
Imagine extending the wall on either side of the droplet. Those extended sections are the dry regions. It's like a sandwich drywall, wet droplet drywall.
Got it. Droplet sandwich. But how does that help them understand the droplet?
This setup allows them to study how pressure and vorticity, that swirling motion within the fluid, behave in a simplified setting, focusing on the region very close to the wall where the fluid's viscosity dominates.
Viscosity. That's the stickiness, right? Like how honey is more viscous than water.
Exactly. And by analyzing this dry, wet, dry setup, they get valuable insights into what's happening inside the droplet as it clings to a surface.
So they're using this simplified model to understand the complex interplay of forces at the droplet's edge. What did they discover about the pressure and vorticity near the wall?
One of the interesting findings is that the vorticity, those tiny swirling motions, can actually change direction near the edges of the droplet.
Change direction. So those little swirls do a U-turn at the edge of the droplet.
Precisely. It's a surprising behavior that influences how the droplet deforms and spreads over time. It's amazing how much complexity is hidden at these microscopic scales.
This whole deep dive has been full of surprises. I never imagined that something as seemingly simple as a droplet could be so intricate and have so many implications for different fields.
It's a testament to the power of fluid dynamics and how it connects to so many aspects of our world.
Absolutely. We've learned about the clever tricks researchers use to model droplets, the unexpected behavior they've uncovered, and the real-world applications of this knowledge. From preventing ice on airplane wings to optimizing crop spraying techniques, understanding fluid dynamics is essential.
And even beyond the practical applications, there's a sense of awe that comes from understanding the intricate dance of fluid happening all around us, from the raindrops clinging to a leaf to the ink droplets forming a perfect image on a page.
This deep dive has definitely expanded my understanding of the world around me. If even a single raindrop holds such complexity, imagine the incredible symphony of fluids playing out throughout the natural world.
It's a reminder that there's always more to learn, more to explore, and more to discover.
So true. Well, that wraps up our deep dive into the fascinating world of droplet dynamics. Thanks for joining us, and keep those questions coming.